Welcome to Food Science and Technology 1, FST 150S. I am Dr. Vusim Shaisa, and today we are going to delve deep into the world of macromolecules number 3, which is lipids. So we've already covered the section on proteins, and we've covered the section on carbohydrates. Now we are going to talk about lipids. So the question is, what do we mean by the term lipid? So the term lipid is generally defined as a heterogeneous group of substances. And these substances are associated with the living systems, which have the common property of insolubility in water, but they are soluble in non-polar solvents such as hydrocarbons or alcohols. So when we look at the lipids nutritionally, fats and oils, they contain around 9 calories per gram, while proteins and carbohydrates contains 4 calories per gram. So what is unique about these class of substances is that they come in various forms. But the most important forms that we are accustomed to in our food products or in our food systems are the fats and oils. There are also other members of this family, which includes waxes, phospholipids, sphingolipids, etc. So now let's talk about the functions of lipids in our bodies and in the foods that we consume. First and foremost, lipids have a concentrated source of energy stored in the adipose tissue. Thus, it provides fuel for our bodies when it is required. Additionally, lipids play a crucial role in the absorption of fat-soluble vitamins, and these include vitamins such as ADEK, which is A, D, E, and K, and thus they ensure proper nutrient uptake and utilization. Another important function of lipids is their ability to provide a feeling of satiety or fullness, helping us to regulate appetite and food intake. But beyond their nutritional requirements or their nutritional roles, lipids, they also contribute to the texture and the flavor of foods, making them an integral part of our culinary experiences. Whether it's adding richness to a dish, providing a crisp texture when we are frying, or enhancing mouthfeel, all these applications include lipids playing a key role in food preparation and enjoyment. But now let's take a closer look at the composition of these lipids. You see, unlike carbohydrates, lipids, they contain carbon, they contain hydrogen and oxygen, but in different proportions. So in general, as I've said earlier on, lipids have a far fewer oxygen atoms compared to carbohydrates, which contributes to their unique functions and to their unique properties. But the question is, what are the building blocks of lipids? Like we did in proteins, we said the building blocks of proteins are amino acids. And then in carbohydrates, we say the building blocks of carbohydrates are monosaccharides, basic sugars. Here we find that in lipids, the basic block of lipids are what we call the fatty acids. And so the fatty acids, in terms of structure, can also be categorized into what we call triglyceride structure. So the basic unit of these lipids is a glycerol molecule. And this glycerol molecule serves as a backbone to which the fatty acids are attached. So now you've got fatty acids consisting of long chain hydrocarbon chains with a carboxyl group at one end, and these are then the building blocks of most of these lipids. So these triglyceride molecules are also known as triglycerols, and they are the most common type of lipids which we found in food and also in the human body. And as I've said, they are composed of 3 fatty acids molecules, which is attached to a glycerol molecule, right? And these This is done through what we call an ester bond. So in proteins, we've got what we call a peptide bond, and then in carbohydrates, we've got a glycosidic bond, and now here in lipids, we've got what we call an ester bond. So these fatty acids, they differ from one another in a few ways. Firstly, their hydrocarbon chains or tails, they vary. Some of them, they've got shorter tails, while others, they've got longer tails. Another factor is a degree of unsaturation. So here what we mean is that the degree of unsaturation refers to the number of double bonds which are present in the hydrocarbon chain. So when we have fatty acids with no double bonds, we say these fatty acids are saturated fatty acids, or we say they are saturated fats. While on the other hand, if you've got one or more double bonds, we say these are unsaturated fats. And so you might have noticed this difference at home. Saturated fats, like those that we find in butter, in lard, they tend to be solid at room temperature. While unsaturated fats, such as olive oil, sunflower oils, they tend to be liquid. We'll ask this question again later on. So the number and placement of these double bonds also affect the properties of the fatty acids. So generally, the more double bonds they are, the fewer the melting points of the fat. This is why you've got oils which are high in unsaturated fats. They remain liquid even in cooler environment. Another important factor now that we need to talk about is the essentiality. So let's talk about essential fatty acids. So what are these? These are fatty acids that our bodies can't produce on their own. So we need to obtain them from our diet. And what are the examples that we can have here? So these include things like, let's say, maybe oleic acid, linoleic acid, linolenic acid. So these are typically unsaturated, and they play a crucial role in various bodily functions. So they are required in our diet. It is also important that we note that the essential fatty acids are predominantly found in plant-based sources, and these will include sources such as nuts, seeds, and certain oils. So if you are looking to have these in your diet, so you need to, for example, ensure that there is adequate intake of these by incorporating a variety of plant-based foods in your diet. So a fatty acid molecule is one of the building blocks of fat. So we've established that fact, right? So we said the more hydrogen than carbon that it has, the more it becomes saturated. So if you look at this diagrammatic representation here, we see that, for example, here there is no double bond in this molecule. So we would say this is a saturated fat because all the carbons, they have a hydrogen that is attached to it here. So it means there is no space for incorporation of another hydrogen molecule. So we will say these, then they become solid at room temperature. And the examples include beef, poultry, coconut oil, palm oil, etc. So if you look at unsaturated fatty acids, so unsaturated fats, normally they contain, for example, they're from sunflower seed or corn oils. These are generally considered as healthier fats. So here, if you look at the monounsaturated fat, which is the most abundant in foods, and it's present in products such as nuts, plant oils, and comprises of the majority of the intake by human beings. We see mono, like we said, monosaccharide means one. So here we see that there is one double bond that is present in these saturated fat molecules. So in other words, it is missing two hydrogen atoms. You can see here there's no hydrogen here, and then there's no hydrogen here, because of this double bond. So this is a monosaturated fat. We also have what we call polyunsaturated fats, all right? So they have more than one double bond. So 1, 2 here. So, and in these we find what we call the omega-3 and the omega-6 fatty acids. So these are mostly commonly found in vegetable oils and mostly in other food oils, as well as in various types of nuts. So the body requires these, right, to keep us alive, to keep you alive and functioning properly. But the same cannot be said about any other types of fats, including monounsaturated fats. So if you look at the sources of monounsaturated fats, vegetable oils, canola oil, olive oil, sunflower oil, and also in avocado. Omega-3 polyunsaturated fat sources include soybean, corn oil, and sunflower. And then omega-6, omega-3 and omega-6 comes from soybean, canola oil, walnuts, etc., as you can see in this table here. So fatty acids also exhibit another important property, which we call isomerism. So isomerism means that the molecule has the same amount of carbon, has the same amount of hydrogen, and has the same oxygen atoms. However, it exists, these are located in different arrangements of atoms of the molecule. So in other words, because of these, they also tend to exhibit what we call isomerism, and then they will have different physical or chemical properties. So unsaturated fatty acids with double bonds can show two types of isomerism or configurations. It can either be the cis transfiguration where they are on the same side, or it can also be the trans configuration which is in the opposite side. So saturated fatty acids here with no double bond, you can also see here, this is this is a carboxyl group. But then here, if you look at this configuration here, which is you've got these molecules which are on the opposite side of the double bond. But if you look at here, we've got these molecules here which are in the same side. So we call this isomerism because the amount of carbon, the amount of oxygen, and the amount of hydrogen is the same. However, the configuration is different. And when the configuration is different, these will then tend to exhibit different properties in terms of their physical and their chemical properties. So I spoke about the chain length earlier on. So the chain length means that the fatty acids chains can either be long or they can either be short. So if they are short chain fatty acids, they give shorter fats with lower melting points. But longer chain fatty acids give longer fats of higher melting points. So the points of unsaturation are due to the absence of the atoms, hydrogen atoms, at the double bonds in the fatty acid formula. Because we can already see here that this is, for example, a representation of a saturated fatty acid molecule. But here you've got one, which is monounsaturated, one double bond. Polyunsaturated, more than one. So you've got a double bond here and a double bond over here. So what are the properties of fats? So the properties of fats is that they are susceptible to oxidation and rancidity. So that is one of the chemical spoilages of fat that happens there. They also have lubricating and shortening properties. They also have whipping properties. They have a high caloric value. So we ask the question, when is it a fat and when is it an oil? It is a fat or an oil depending on the state. So the name indicates the state of the material at room temperature. So if at room temperature the material is solid, we would say it is a fat. If it's an oil, we would say it is a liquid. If it's a liquid, we'll say it's an oil. So in some cases, it may be desirable that we convert these liquid oils into solids at room temperature. So the greater the degree of unsaturation in the fatty acids, the shorter the fat and the lower the melting point. So with a considerable degree of saturation, the fat, of course, I said, it will be a solid at room temperature. So what we can then do, because of the points of unsaturation, chemically hydrogen atoms can be added to oils because they are unsaturated. And so what we can do, we can add these hydrogen molecules to saturate the fatty acids. And this process will convert the oil to a solid at room temperature. And this process is called hydrogenation. What is hydrogenation? It is that process that can be used to convert liquid oils to solid oils at room temperature. So it converts the vegetable oil into a solid shortening. So we can have what we call partial hydrogenation, which results in intermediate solidification of the oil. So unsaturated fatty acids are prone to oxygen attack, or in other words, they are sensitive to oxygen at the oxidation at the point of unsaturation. So what happens is that hydrogenation then saturates the fat and makes it less prone to oxidation and more stable against oxidized flavor development. So the other class of fats that we find, as I said, we've got phospholipids. Because of their polarity, these phospholipids, they contain positive and negative charges at one end of the molecule and non-polarity on the other. So this makes them good emulsifiers, and they are used in the food industry in products such as chocolate, salad dressings, mayonnaise, to help keep the polar and non-polar components together. Remember, we've already spoken about this concept of emulsification. So these are molecules that can then be able to perform a function of emulsification because they've got both the non-polar and the polar ends. So when we look at waxes, what are waxes? So waxes are molecules that are not made from glycerol, but from fatty acids and monohydric alcohols of 24, maybe to 26 hydrocarbons in length, right? So their function is to prevent evaporation of moisture or invasion of tissue with water from the environment. So in the food industry, they are used in some packaging and as ingredients in some confections and candies for texture and appearance. So waxes are non-digestible. And so the other molecules that we found is sphingomyelin. So sphingomyelin is a sphingolipid, and it is an important constituent of nerves and brain tissue. In this lipid, glycerol is replaced by a long-chain nitrogen-containing alcohol. We also have sterols. So there are a number of sterols that are important, have important functions in the body. And they have a complex chemical compounds containing of sometimes alcohol group, which a fatty acid can be esterified. So the sterol in cholesterol is involved in the composition of biosalts, we know from biology, which play a role in the emulsification of fats in the intestine, hence the digestion of fats. We also have egosterol, which is another sterol that may be converted to vitamin D in the body under the influence of sunlight or vitamin D. So the properties of fats can be categorized into three groups. So we can have sensorial properties, functional properties, and also nutritional properties. So in terms of their sensorial properties, they contribute to the richness and mouthfeel of food products, providing a satisfying creaminess that enhances our flavor perception. So here, if you think of the texture that is made from salad dressings or the indulgent taste of a perfectly buttered croissants, so that is as a result of these fats that are used today. So additionally, if you think about it, fats and oils, they carry and they also enhance the flavors of other ingredients, making them crucial components in many food products. Whether it's the aroma of a sizzling bacon or the subtle nuttiness of olive oil in a homemade pesto, these sensorial properties or these sensory experiences are often what makes our meals memorable. So if you look at the functional properties here, we look at heat transfer, shortening, emulsification, whipping properties, lubrication, plasticity, and melting point. And then in terms of emulsification, they play a crucial role in emulsification, helping to create stable mixtures of ingredients that would otherwise separate, because we know that water and oil, they do not mix together. But fats, which contains both the hydrophilic and the hydrophobic groups, then they are able to perform this emulsification function. And this is evident in salad dressings, in mayonnaise and sauces, where fats and oils serve as the binding agents that bring together these disparate components into a harmonious whole. If you look at the nutritional aspects, they've got a high caloric content. They are vitamin carriers, for example, fat-soluble vitamins, and they also provide essential fatty acids. So while they have long been vilified for their calorie density and association with certain health conditions, but fats and oils are essential nutrients that provide a range of important functions in our body. In terms of functions, so we can have nutritional functions, sensorial, heat transfer, shortening, emulsification, whipping, and plasticity. Those you can read from the table here. Melting points like in cocoa butter. So let's look at some of the applications. So what we food manufacturers require from products such as butter and margarine is that they must exhibit a plastic texture or consistency that remains spreadable even when the product is refrigerated. Yet what happens is that the product should not excessively soften or melt at high temperatures. For example, when it is hot on a hot summer day. So therefore, achieving this balance involves a careful selection of fat compositions and processing techniques to control the crystalline structure and the melting behavior of the product. So if we look at salad oils, a key requirement for salad oils is that it should be clear, or let's say maybe the clarity or the pourability. So the oils that are used there, they should remain clear and free from any suspended particles or cloudiness, so that they can be aesthetically pleasing for the consumer in the final product. Therefore, achieving this clarity involves a refining process that removes impurities and undesirable components in the oil. So that's very important, right? Additionally, it must, for a salad dressing, it's important that it has a low tendency to crystallize or solidify when it's subjected to refrigeration temperature. So it should also remain a liquid. So the presence of molecules with high melting points can lead to unwanted crystallization. Therefore, you need to make sure that those are not present in your food products, right? Because they're going to disrupt the stability of those emulsions that you have formed. And what they will do is that they will result in phase separation. So you need to carefully select the type of oils that you choose or the type of fatty acids that you choose for different applications. So in chocolates present a very fascinating interplay of structural integrity and sensory indulgence, and these are governed by the unique properties of the cocoa butter and its substitutes. So in Food Project 2, you are going to manufacture a food product based on chocolate and confectionery applications. So a chocolate should not melt at room temperature. It should be brittle and melt in your mouth. And the component that gives chocolate these characteristics is the cocoa butter, which melts sharply at 30 to 36 degrees Celsius. Because at the heart of these characteristics is cocoa butter, because it's a complex mixture of fatty acids that exhibit a sharp melting point between 30 and 36 degrees Celsius. And this narrow melting point range of 30 to 36 ensures that the chocolate that is produced remains solid at room temperature, but it melts in your mouth upon contact with the warm mouth when you put it in your mouth. So in certain applications, therefore, where maintaining the shape and the stability are important or paramount, such as, for example, in biscuits, it is important alternatives to cocoa butter may be utilized. And these alternatives or substitutes must possess higher melting points to prevent premature melting, ensuring that the chocolate coating remains intact even when we held it in our hand. If we hold it in our hand, it should also not melt. So we can already see that these fats and oils, they've got different or maybe versatile functionalities which we cannot find in carbohydrates and which we cannot find in proteins. So it is important, therefore, that we understand that achieving this desired functionality involves, in most cases, the incorporation of specialized fats and oils with tailored melting points. So I think I want to pause here for this short clip. Let's meet in the next section. Thank you very much.